We're going to transition here into our next speaker. Our next speaker, again, is part of the groundwater track. And our sponsor for this talk, again, is Extension Lakes. Extension Lakes is a partnership with the College of Natural Resources at the University of Wisconsin-Stevens Point. For those of you who may be just joining us, this morning's session has a strong focus on one of the more widespread groundwater, if not the most widespread groundwater contaminant in Wisconsin's groundwater. And our next speaker will be focusing on that topic as well. His talk is Nitrogen, Groundwater Quality in a Changing Climate, Intersecting Challenges for Wisconsin Agriculture. And our speaker is Dr. Christopher Kucharik. Chris Kucharik is a professor and department chair at UW-Madison in the Department of Agronomy and the Nelson Institute Center for Sustainability in the Global Environment. He has affiliate appointments with the Department of Atmospheric and Oceanic Sciences, Agroecology, the Center for Climatic Research, and Freshwater and Marine Sciences. He is also a member of the Research Council for the Wisconsin Initiative on Climate Change Impacts, otherwise known as WICI, and he serves as co-chair for the WICI Agricultural Working Group. His research program uses fieldwork and numerical modeling to understand the impacts of climate change in land management on ecosystem goods and services, and is going to be a great speaker to kind of highlight both the current status of nitrate challenges as well as what we might be able to expect moving forward. So with that, Chris, I'm going to turn it over to you.
Great. Thank you, Kevin, for that introduction, and welcome everybody this morning, especially those joining on Wisconsin Eye. Thanks for tuning in. So the first thing I want to do as we get started here is just take a brief review over what the extent of agricultural land is in Wisconsin. These two snapshots on this slide just show, basically how prevalent agriculture is across our southern, central, and then some of our north central portions of the state, and the types of crops that sort of dominate that landscape. We grow a lot of corn, soybeans, wheat, and there's a lot of other specialty crops that Wisconsin is known for, particularly in the Wisconsin Central Sands region, which is a very important potato and vegetable growing region. Now, because of that, the agriculture and these crops do require a significant amount of nitrogen fertilizer, and this is a nice graph just showing what the typical recommended amounts are for those cropping systems. And if you look out on the far right of that curve, you'll see corn, potato, sweet corn. Some of the more prevalent crops like corn require the most, unfortunately, to produce those high yields. And unfortunately, the recommended amounts for cropping systems don't eliminate the risk for nitrate leaching into our groundwater. So in this slide, I'm just showing for corn, just showing a particular what we refer to as phenological development, or how the crop is developing, with some nice photos there of what you might see in certain areas of the Wisconsin landscape in May, July, August, and then the rest of the year after harvest. And unfortunately, there's only a very short time period during which there's active nitrogen being taken up by this type of a crop. And even then, so corn, for example, only takes up about 40 to 60% of the fertilizer that's actually applied. So you have a large amount of days during the year when there's no nitrogen uptake from the soil by these cropping systems, and that the nitrate leaching potential is quite high because of that. And that has led to a variety of water quality issues across Wisconsin. You've probably seen the headlines. These are just some of the few that have happened in some of the local papers around the state, as well as the New York Times back in 2018. And we know from data that's being collected that the nitrate concentrations in wells are quite high, and many of those are above the 10 parts per million EPA standard set for safe drinking water. The patterns on this map are obviously related both to the agricultural land use that's ongoing, as well as differences in soil types that we have. And if you were to overlay the agricultural land extent with data that's been collected on those nitrate values, you'll see that about 20% of the samples that exceed that EPA standard level are in areas where more than about 75% of the area is cultivated, unfortunately. So that's presented, a current and historical challenge and sort of a buildup, as decades have gone by, basically since the end of about World War II, when nitrogen fertilizer was introduced as a means to help increase crop productivity. But also at the same time, we've seen climate changing across the state. And I'm going to go through and just highlight previously, what we've seen, where we're going to the future, and try to connect that back to the challenges that farming faces and how things will get difficult moving forward. I just want to make sure that I acknowledge that a lot of these data and slides that I'm showing in this part of the talk came from Dan Weimont, the Nelson Institute Center for Climatic Research, as well as the Wiki Climate Working Group. So if we look at the 4 seasons, these figures are showing by basically crop reporting district, 9 of them in the state, what the overall temperature trends by season have been over the last 70 years or so. The asterisks represent statistically significant trends. So we see that the most significant warming has happened in wintertime, with somewhat of a lesser extent in summer and in fall. And if you split up those trends and look at the differences between day and night, you can see that wintertime at night has by far had the most significant change, upwards of 5 to 7 degrees Fahrenheit of temperature trend over those 70 years. And to a lesser extent, summertime during the day, where the warming has been a little more muted, only about 1 to 2 degrees over that time period. Nonetheless, still warming across all these different segments that we're talking about. So something that you may be more familiar with because it's maybe impacted you personally, or if you're a farmer and you've been dealing with this, the overall trends in precipitation during these 4 seasons. And these trends run out to 2018, again, by crop reporting district, climate reporting district across the state. So wintertime in the central and the southern portions of the state, very significant increases in precip, about 15 to 20%, as well as in summertime. But you'll see there's a lot of spatial variability. Portions of the north central and far northern parts of the state have actually seen somewhat of a decline in precip over that time period, although it hasn't been statistically significant. And those significant increases during, let's say, winter and spring in the south and summer over the southern and central portions of the state overlie many of the agricultural regions in the state where we have the most concentration of agricultural land. This is one figure I've thrown together and used previously, just highlighting what's going on at the reporting station in Madison. Each of those dots represents the 30-year average precipitation, so the preceding 30 years up until that individual point. And you can see since the 1960s that the area has seen almost a 25% increase in precipitation. And if you look at the top 10 wettest years on record, just looking at Madison, you'll see a lot of those have happened just in the last 5 to 7 years, 2013, 2016, 2018, and 2019. And as well as there being an increase in the mean annual rainfall, we've seen extreme rainfall events happen more frequently. And this is a very telling figure that Wisconsin has experienced at least 20 100-year rainfall events. So something you would anticipate would happen once every 100 years have happened just in the last 10 years between 2011 and 2020. And the highest risk for those heavy rainfall events are occurring in areas that, again, have the highest concentration of agricultural land, or if you're talking about the driftless area in southwest Wisconsin, land that has the most topography, where runoff and erosion is more prevalent. And you can see a lot of these numbers are, really extreme, in the order of 5 to upwards of 11 or 12 inches in a 24-hour period. So in the future, we're generally expecting we're going to get warmer. That depends on what type of a scenario plays out, or what climate models are suggesting how atmospheric CO2 and other greenhouse gas emissions play out. But by the middle of this century, upwards of maybe 3 to 9 degrees of warming. And then by the end of the century, depending on that scenario, anywhere from 3 degrees of warming upwards of 16 degrees of warming. Those are very obviously significant changes that are going to happen. So future rainfall projections, this is where the models don't necessarily agree, all the time. You see each of the lines on each of these graphs, we refer to these as like spaghetti plots. There's quite a bit of variability. The solid dotted line represents the mean of those models. And so by sort of on the low end, by 2050, maybe we suggest a 10% amount of increase in rainfall precipitation during winter, spring, and fall. Not so certain, what's going to happen during summertime. And then by the end of the century, in the most significant type of business as usual scenario, 15 to 20% wetter in winter, spring, and fall, and not quite as much increase or certainty during the summertime. We also know that the increase in frequency of heavy rainfall events or extreme events will go up. So the chart on the figure on the left there is just showing the typical number of days per decade where daily or 24-hour precipitation was greater than 2 inches. The figure on the right shows the middle part of this decade and sort of the number of events. So you see a slight increase in the likelihood that you might see an additional 1 or 2 events per decade that are 2 inches or greater. So what does this mean to, protecting our soils and water resources? So the first thing is that, it's gonna, in terms of fertilizer and manure management, if it hasn't been hard already to keep nutrients in place in the root zone or out of surface waterways and groundwater, it's gonna get increasingly more difficult as those changes in precip continue. Some other people might be thinking about irrigation management. Hotter, maybe drier conditions during certain points of the summer may increase crop water demand. There might be more abrupt changes in surface water levels, kind of like what we've seen probably in the last 2 decades across portions of the state. And then with soil management, there might be more flooded acres, more erosion, more tillage, and planting operations might be more challenging to farmers. So the bottom line is that more challenges will persist and probably increase, unfortunately. One other thing to consider is that those warming temperatures that we have will warm soils, and that could promote more rapid decomposition of the litter that happens to go back to the soil after a harvest or just naturally. That might increase nitrogen available in the soil due to nitrogen mineralization. Warmer temperatures during winter tend to promote more freeze-thaw cycles. So while that might mean also more potholes for those of you driving around, it also complicates what soils are doing too. We might have times when we might see more infiltration and drainage during wintertime. Warmer temperatures during winter can also increase the likelihood of rain falling rather than snow. And all these things can add up to additional drainage and loss of nitrogen that's stored in the soil profile, making it down into the groundwater system. So I'm presenting these intersecting challenges. The story is there's too much nitrogen in the system. We have increasing rainfall and extreme weather, making nutrient management more challenging for farmers, which is increasing the likelihood that nitrogen is going to leave the root zone and find its way to our groundwater. So what have been some of the responses to this point of farmers to wetter conditions? And this is just a select few. So the first thing is that they're generally adding more nitrogen fertilizer to make up for the increased risk of leaching losses. These quotes I've pulled out of a publication from 2019 that was published on farmers' perceptions of climate change in context. And if you sort of follow some of these, it's just basically farmers do get worried that as rainfall increases, they're going to lose more N from the system, which is going to drive their yield potential down for crops. And the response is to add more nitrogen back to the system to make up for that perceived risk of loss. Unfortunately, that's kind of a double negative. We obviously are, want farmers to do what they need to do to remain viable and to produce a crop. At the same time, they're at the mercy of Mother Nature, and there's only certain things that they can do without knowing really what's going to happen with the weather. We've also seen a shift across the upper Midwest to more drain tile being put in. This basically short circuits the natural hydrology of the system, or the way water moves through the system. This can be both problematic to moving more in more quickly through the system, either to surface waterways or potentially making its way into other sources of water, groundwater. And you might, be seeing some of this on the landscape. The extremely wet decade that we had in Wisconsin from 2011 to 2020, the wettest ever on record, created a lot of more groundwater flooding, basically where the water table was brought closer to the surface. It's created new lakes in the landscape. This is just a photo of me standing next to a flooded field north of Madison near Arlington. These scenes are very persistent across many regions in the southern and central parts of the state. And since we went into that wet period around probably about 2008, we haven't seen a lot of those fields dry out, unfortunately. So this is just one other aspect of the challenge that has been presented to farmers across the region. So how might we develop recommendations to solve some of these problems? So my group in particular, and then there's many others throughout the university system in Wisconsin, as well as our extension folks and others, we in my lab in particular study the intersection of ag land management, weather, nutrient management, and groundwater quality. And we do this through using field experiments on the landscape, where we're manipulating things, measuring things that are coming out of the system. Either it's yield, maybe it's nitrate leaching and drainage, how much water is being used for irrigation. And we also use numerical modeling tools that allow us to do things that we can't do in fields with experiments. And I'm going to go through a few examples of these. So these are just some photos showing, what typical field work might look like during the growing season. And these are, folks in my lab, graduate students and postdocs, in particular working in the central sands region of Wisconsin. Has very sandy soils and is more prone to losing nitrate to groundwater, unfortunately. We're working directly with farmers in their backyards. In particular in the central sands, we worked with Isherwood Farms quite a bit. There's other farms that we're working with, so we can understand, directly, how their management is playing out and what types of decisions they're struggling with. And in the case of some of them, they're very active in doing the research with us, which we greatly appreciate their time and effort and involvement to help solve these problems. I want to focus a little bit on a specific measurement that Kevin Mazar has actually been making as part of his PhD research, and that's measuring the nitrate leaching and drainage out of these systems in the central sands. There's a picture of Kevin there in the center with an equilibrium tension pan lysimeter, which is probably the gold standard for making these measurements. It's not easy work. You've got to bury the lysimeters, below the root zone, a typical root zone for crops. There's a lot of plumbing involved and tubing and maintenance of these systems, but they give us a very good understanding of what is actually leaving the system at a pretty fine temporal scale, let's say weekly or biweekly during the growing season. Here's some of Kevin's preliminary data, just to give you an idea of what we're seeing. He's been following a complete rotation in the central sands. These are 4 years of data, starting in 2016, going through 2019, and showing what the cumulative nitrate leaching is beneath sweet corn, potatoes, field corn, as well as peas and pearl millet. You'll see quite a bit of variability. The amount of nitrate N that's being leached in pounds per acre, for sweet corn, these data are suggesting, 135 pounds per acre, and as low as 46 pounds per acre for peas. And there's a direct relationship there, not only to the amount of N that's being put on for those crops. So sweet corn, potatoes, and field corn are more nitrogen demanding crops. They have more N being put on, so they're more prone to leaching more out of the system. Peas and pearl millet don't have that, but are still, as you can see, still leaching a certain amount due to N that's being stored in the system. The other thing I want to note is that the amount of nitrogen that's being lost from those systems, while it's happening during the growing season, in many cases, there's a significant amount that's happening outside of the growing season, which goes back to some of the points I was making earlier about the active period of nutrient uptake in some of these systems where the crops are only in the ground and actively growing, let's say from May through late August or early September. The other thing we're looking at, again in the central sands, is irrigation. And as you've seen, there's nitrate in that water. Farmers are then pumping that water to irrigate their crops during the growing season. And there's a certain amount of nitrate then that's being fed back to those crops from that source. And we really should factor that into nutrient management as best as we possibly can. And the first step to that is getting a handle on how does the nitrate actually vary during growing seasons, as well as from year to year across a wide extent of the geography in the central sands. And this is a pretty busy figure, but I'll walk you through it. This is data that some of my graduate students, Tracy Campbell and Emily Heineman, have been collecting over the last 3 years. So the first thing is that there's 3 years of data being shown, and those are labeled up at the top of the figure. The different colors represent different places on the landscape in the central sands. And then the different letters within that just represent different fields or different wells that were sampled. So you can see a wide range of variability in terms of what farmers are putting on in terms of the amount of nitrate, nitrogen to their crops through irrigation sources. You'll notice that as we've seen with some of the other data, these numbers are well above 10 parts per million in many cases. The overall average from this data set is 20.1 parts per million over 3 years. But what we do know is that there's consistency from year to year for a particular farm, as well as individual wells from that farm. And there's more variability across space. So this means that somehow we're going to have to do a better job or a good job of helping farmers figure out exactly what might be coming out of their wells and how to factor that into the management of whether it be corn or potatoes or other crops that are being grown with those irrigation sources. So it was just a sort of a little bit of an insight into the field data, types of things we are studying on the nitrogen cycle and nitrate leaving the system side of things. The other part of our work is using numerical models. And what is a numerical model, or an agroecosystem model? So it just represents the growth of plants and the cycling of carbon and energy and nutrients in the soil plant atmosphere system. And these types of models inform us how crop yields might respond to weather variability and irrigation and nitrogen fertilizer management. They can inform us how much nitrate might be lost due to a function of that management, the weather variability, as well as the soil variability. And we can't just learn everything from our field work, unfortunately. So models allow us to examine a combination of scenarios that wouldn't be possible. It also allows us to look at their impacts over large spatial scales and long time periods that allow us to examine different scenarios of change that have relevance to policy decision making in Wisconsin, or at least we hope that that work can help guide legislators and others working, let's say, for DATCAP or the DNR, decide what we might be able to do and where you get your biggest bang for your buck in terms of the types of changes that might need to happen. So the types of questions that you might be interested in asking might have to be, with manure spreading, if we do split fertilizer applications and the amounts, if we adopt planting cover crops, will that have some type of an impact on reducing nitrate leaching to groundwater? And there's other questions that we can explore, including, very impactful transformations of the landscape to types of systems that aren't even existent right now, sort of outside the box type of thinking. The other thing that those models help us do is to build our understanding of nitrate leaching and yield responses better. And this is just one type of an example that you might see for a typical numerical simulation, where the green line is showing the typical, yield response that you both would see in the field as well as with the model, sort of what corn yield might look like depending on how much fertilizer, manure, nitrogen is applied. But what's often missing, with recommendations is that red line. What's the nitrogen loss associated with the decision making? We don't have that type of information available right now, really to anyone. And when we're trying to figure out what the optimum N rate is, you have to consider its impact on yield, the cost of the fertilizer, as well as the leaching loss estimate that offers the best protection of groundwater quality. Obviously, we'd like to see that number be zero, but that's not always going to be possible. But where are those intersecting lines going to happen that makes a farmer profitable as well as protects our groundwater for years to come? One other type of tool that we're using, and this builds upon the more sophisticated and complicated numerical models that we use, is development of simple decision support tools. So the idea here is to educate. And what does this particular tool do? And this is a current project that we have with DNR support, is to think about building a tool that people can latch onto, go to a web portal, make some decisions about what they're growing, where they're growing it, what the type of yield potential would be for that crop, what the amount of fertilizer is that's not only recommended by extension, but maybe what they're practicing, and start to play around with that to see what the amount of leaching might be, as well as what the maximum return to nitrogen is. Basically, what's the profitability based on those decisions that the farmer is making. Now, in the simplest sense, this is simply a sort of a checkbook type of method that's looking at the inputs and outputs of nitrogen balance based on the decisions that someone might be making. What we want to do is use the more sophisticated modeling output that will be running across the state over the next couple of years and get that into what is referred to as a Shiny app, something that's done behind the scenes to help advance those nitrogen decision support tools so they can be more widely applicable over a wider range of conditions and future climates for the state. So I think what we need to be thinking about is outside the box ideas in agriculture. I think we know, and there's pretty good data to suggest that simple adjustments to nutrient management practices may not or will not fix the water quality issues in a reasonable amount of time. We've seen this from other data sets. We know that the simple tweaks, whether it might be simple, management practices or changes to the amount of nitrogen and timing of that, may not have the big effect that we need. And outside the box means transformation of agriculture to something that may be uncomfortable for some to accept, but it might be what we need to do to actually clean the water up and not have to wait long time periods. Unfortunately, this is not going to be any easy fix or quick fix to the problem. We know that due to legacy nitrogen, which means due to decades of previous land management, nitrogen is built up into the system. And even if we shut off the amount of fertilizer that's going on today and made it zero, it might still take 10, 20, 30 years before we'd see an appreciable change and decline in nitrate in many regions to get, let's say, groundwater below 10 parts per million in areas where it's well above that value. I've discussed a little bit about the changing climate and how that's going to prevent rapid progress also. That's obviously going to challenge farmers and others to manage nitrogen and keep it where it needs to be and to be taken up by plants. So some of the questions that still need answers, how do we actually define water quality improvement? I think the state needs to think about this pretty carefully. There's probably places and locations where we can move the needle, so to speak, on getting those values lower. There might be other places where it might be relatively difficult, depending on what's being suggested in the current system, to move from 40 parts per million to 10 parts per million or lower. And if that is the goal, that the expectation should be that farmers are not going to be able to do that in a few years. It may take 2 generations worth of change to actually make that happen. And that gets to the question of, what is the magnitude and location of land management change that we might need to improve water quality? There's a lot of things we know, a lot of things we don't know, and an impact of a changing climate makes a lot more unknowns than knowns probably right now. So getting back to the question of, how might agricultural systems need to be transformed in the long term to meet water quality goals? We know by enrolling more folks in CRP, transforming the landscape to more perennials, using cover crops. There's certain management practices we know will have a much higher and more significant impact on reducing that nitrate leaching loss. Unfortunately, a lot of those ideas right now may not be financially viable for farmers to adopt. They might be down the road, which brings me to the last point, that long-term plans that we're making right now have to have gradual changes built in that will allow farmers to adapt. We can't expect them to make drastic changes in a short period of time. We've already seen a significant loss in the number of dairy farms, let's say, in the state of Wisconsin over the last couple of decades. We'd like to see, more and more small farms remaining in business. But a lot of times, if we start regulating and making them adopt to certain practices and regulations that are too stringent or significant for them to adapt to on a short time scale, it may just drive them out of business. And they may walk away from farming, and we don't want that. So we need those farmers at the table as part of this decision making and process that goes on. So I'm going to end it there, and I've tried to leave at least, it looks like we got about 10 or 12 minutes for questions. So thank you very much for tuning in and listening.
Thanks, Chris. For everybody joining us through Wisconsin Water Week, please feel free to monitor and enter any questions that you have for Chris in the chat feature. As we receive questions, we'll try to answer those as best as possible. And Chris, there are a number of questions coming in now. One of the ones that came in pretty early in your talk, which you kind of expanded on, but I think is worth maybe reiterating, giving you a chance to elaborate on. It says a key question for the general public is, how do you get both surface and groundwater with significantly lower nitrogen pollution and the traditional crops grown by farmers in Wisconsin? So just elaborating on maybe some of the challenges with the current cropping systems that we have meeting those goals.
Right. Yeah. Well, unfortunately, there's a couple of things that can be done. First, probably an actual reduction in the total amount or mass of nutrients that's being applied to the landscape, or you make decisions to transform the system into one that doesn't require as much N. And there's certain talk right now suggesting that going back to more perennials on the landscape, rotational grazing, as part of our systems in the state, America's Dairy Land, would be a way And we can effectively show that, particularly through modeling, that over a 30-year period, if you transform large portions of the landscape back to more grasses and that, and away, let's say, from more row crops, you can effectively manage that nitrogen and keep a lot of it from entering groundwater or surface waterways. And there's other ideas too. Cover crops are largely unexplored. Other types of management, maybe within the season, interseeding, certain types of plants within crops that are growing. But I think largely that the large scale transformations and getting more people to adopt and buy in are really are the keys. But again, it won't happen in 5 to 10 years. I mean, we're talking about a few decades down the road.
And you and I have talked a number of times about how, uh, from a science standpoint, we're able to recommend what would work, but a lot of times it's might be more difficult to actually implement given societal preferences or political considerations. But I think a lot of your modeling work does have some key lessons that communities can use to understand what we know might work. Doesn't always mean it's easy though.
Right.
Another question here. A lot of people joining with some interest in lakes. Can you maybe comment a little bit on how nitrate in groundwater contributes to plant growth in lakes? And obviously, groundwater and surface waters have a pretty strong connection, but specifically, anything you can provide in terms of nitrogen role and impacts to plant growth in lakes in Wisconsin?
Yeah, yeah. I mean, the impact as a nutrient and a fertilizer doesn't really matter whether you're growing the plant on land or if it's growing in water, unfortunately. And I think the largest example and connection that I can say is the connection of what goes on in the Mississippi Basin. That sort of map that's a subset on the slide here behind me, just showing extent of agricultural land in Mississippi as well as the cities are in red. But any of that N that leaves the landscape or phosphorus, in our certain parts of our state, make its way down the Wisconsin River to the Mississippi, down to the Gulf of Mexico, create these hypoxic zones or dead zones, unfortunately. And you see a lot of local effects, in area lakes, algal blooms and things like that. A lot of people point to the phosphorus problem, but you can't forget that nitrogen comes along with that too. And the two of those are not a great recipe for promoting clean water, unfortunately. So there is a very tight connection to that.
Another question here about legacy nitrogen, and that's the nitrogen that's kind of been built up in the groundwater system over the years due to that lag time between what happens on the land surface and the groundwater quality below. But more specifically, in terms of legacy nitrogen in groundwater, having been measured and estimated in some of your research projects, or so the question is, has it been measured or estimated in some of your research projects, or how has it been incorporated into the agro-IBIS modeling that you might be doing?
Right. Yeah. So, yeah, that takes the modeling to an entirely different level, which I didn't talk about here. But some of the work that we're doing is coupling the agro-IBIS model, which is basically above the saturated zone, and connecting that model to another model that represents groundwater and groundwater flow beneath the surface, which really isn't done. It's a very difficult problem numerically to do, but then you have an explicit connection between things that are going on the land surface, whether it be the amount of nitrogen or phosphorus or something that's being added, changing climate, and how that starts to affect the groundwater, and then vice versa, how the plants might start taking up, or how the irrigation is starting to feed into what's going on above ground. So yeah, it's done more through another modeling approach that accounts for the whole system. But I'll also add that, yeah, those data that we're collecting out there both help us calibrate our models, check them, and validate them to make sure that they're working correctly. And then, like the nitrate in the irrigation water, we wouldn't be able to do a good assessment or simulation of a system if we weren't accounting for that. So up until this point, we'd just be sort of guessing if we didn't have those data, and those data allow us to more accurately input those values into the model to do a more precise and accurate simulation.
Another question here about the the decision support tool that you mentioned and kind of showed a screen capture of, and whether or not that information will be incorporated into some of the existing tools like Snap Plus, or what the ability of some of those tools to be used by regulatory agencies or maybe farmers moving forward.
Yeah, there is, planning and, discussions will happen between, those that are working with developing Snap Plus, to hopefully maybe it's some type of a bolt-on type of module to Snap Plus that would be able to spit out, if you make this decision with nutrients, this is what the likely leaching potential might be for that decision, depending on where you are in the state, what your soil type is, what your typical management is. So yeah, that is being thought of, and that would be our hope, that you could use the tool separately, or it may be able to feed into something like a Snap Plus eventually.
So another question here, maybe about modeling of various scenarios. And this one in particular mentions cover crops, and whether there's existing research or indications that cover crops will reduce the amount of nitrogen leaching to our groundwater. So maybe I guess the question I'd have maybe from a general perspective is why we might assume cover crops would reduce nitrate leaching losses, and then how that information might be used in a model like AgroIBUS.
Sure. Yeah, so, cover crops, the thought of planting something that greens up after your summer crop comes off the field would extend, the amount of time that there's something actively growing out there, and taking up nitrogen. Because some of the N that's applied, within growing season may not get taken up by that particular crop that's being grown, may be stored there, and then it's prone to leaching outside of the growing season once that ends. So a cover crop could come along and maybe help take up some of that residual N that's left over. The challenge that we have in Wisconsin is due to our climate. Sometimes it's difficult to get a cover crop to establish and grow before winter comes along. So states further to the south and west of us probably seen a little better, you want to say, growth and sort of ability to get those established. But I would say with a warming climate in Wisconsin, farmers may have a decision to make on whether they adopt a longer season corn or soy hybrid to take advantage of the longer growing season, or keep planting the same and have a better chance at having a cover crop establish and take up nitrogen from the system after the fact. So yeah, so that's just sort of getting at those two ideas.
And I think we have time for one more question, and this one I'm going to pick because I think it focuses a lot on your strengths of the intersection between agriculture and this climate change issue. The question is, do you expect the changing climate will cause a global shift in where desirable farmland is located? And if so, in what ways?
It's a good question. It's one that I've heard discussed, in particular, like in Wisconsin, as well as the Midwest. And I think to some extent that might happen. It's very hard to pick, exactly how certain climates are going to change. Sometimes people, you may have seen, future climate in Wisconsin is going to look like Arkansas or something like that. Well, it's hard to pick a specific analog like that, but people do have to remember, as temperatures warm and sort of certain zones move further north, like if you take like the hardiness zones that the USDA puts together, the problem is that soil development goes hand in hand, with certain types of vegetation types, and that if you look towards like northern Wisconsin, well, first of all, I do not think we're going to cut down our forests to support agriculture, and those soils aren't necessarily the best for supporting agricultural land management and land use. So It might happen in some regions, but it's not an easy solution elsewhere. So I don't think you'll see it necessarily in Wisconsin unless it becomes, I guess acceptable to be transitioning some of our beautiful northern hardwoods to more agricultural landscapes.
Thanks. We're going to have to leave it at that. I just want to extend sincere thanks, Chris, for joining us and sharing your information with us. Thanks to everybody joining us for Wisconsin Water Week, as well as everybody joining us on Wisconsin Eye. We do have a short break here from 9:30 to 9:45. At 9:45, we'll be resuming with some sessions on PFAS, as well as salt or chloride in our lakes, rivers, and streams. Please take some time to visit our exhibitors if you're joining us for Wisconsin Water Week. And we'll adjourn the session and look forward to seeing you at 9:45. Thanks, everybody.